So I'm, excuse me, I'm Dave Soper from the University of Oregon, and our speaker is Bryan Weber from the University of Cambridge. He's going to tell us about why we think there's physics beyond the standard model. And I should just say just a tiny little bit about Bryan. He's a very distinguished particle theorist who's been in this business for quite some time. He's probably best known as the originator, with a couple of collaborators, of a computer program that's known as Herwig. That program is used to simulate events at the LHC and previous accelerators. There's now 3 of these things in similar kind of programs in basic use, but Herwig was one of the first 2. And it contains inside of it detailed modeling of how particle physics works. And I think it's fair to say that if all the copies of these 3 programs were to disappear somehow by magic from the face of the Earth, the LHC would just have to shut down. It could not exist. So we're now going to learn about physics beyond the standard model and why we think there is some. So, Bryan Weber.
Thank you very much. So I'm still recovering from the cold that you can hear that Dave has, so I hope my voice won't give out during the talk. So yes, I'm charged with the job of trying to explain to you why we think there's something beyond the standard model. As you've heard in the previous talks, we have now a complete model of a wide range of phenomena, which is an internally consistent mathematical theory, and we can use it to compute with incredible precision. But we know perfectly well that it's not a complete theory of nature, and I'll try to explain why. So my outline is going to start with the problems of the standard model. That is, what we don't like about it conceptually, and also what it certainly doesn't explain about the universe. And one of the most important things, as you've already heard, is dark matter. There is a lot of stuff in the universe which is not explained by the standard model. Another very interesting conceptual question, now that we know that the standard model contains 3 distinct kinds of interactions, as we've heard, it's a product of 3 so-called gauge theories, and we would like to understand whether these 3 are part of some overarching unified theory. So in particular, do these forces of nature unify in some way? I'll try to explain what that means. And then we'll see that from many points of view, these things point towards possibility beyond the standard model, which is called supersymmetry, which would cure some of these problems and makes very interesting predictions for the LHC. And you will hear in the next talk, I'm sure, about searches for the predictions of supersymmetry. Now, this is already quite a challenging menu here, and I may not have time for another topic here, which is about the masses of the neutrinos. This is also something which is not explained by the standard model, certainly, but on the other hand, it's not so directly related to the Large Hadron Collider. So although it's a very challenging problem, it's one that doesn't impinge too much on the program of the experiments there. So we'll see what time is available for that. So let's look at the standard model yet again. Here's the list of particles in a slightly different format perhaps from what we've seen in the previous talks. I just remind you that we have the so-called matter particles here, the quarks and leptons, 3 families of each. And then we have the force-carrying particles, which mediate the forces between these matter particles. And now we finally know that we have in addition, the Higgs boson, which is what you would call the mass provider, the thing that enables some of these particles to have mass. Now, this, in terms of the terminology of the subject, there are interactions which are classified as either electroweak, which are shared by these particles outlined in green here. So what happened to my point? Yeah, here it is. So all these particles interact through electroweak interactions. That is a combination of electromagnetism and the weak nuclear interaction. And then some of them interact by the so-called strong interaction. That is the quarks and gluons, which make up atomic nuclei. And in terms of the terminology of the symmetries that Laura explained before lunch, the strong interaction is technically called quantum chromodynamics. It's what we call an SU3 gauge theory. This is the technical term for the symmetry group associated with that symmetry. And the electroweak has two components, SU2 and U1. These are going to be two separate couplings associated with these two symmetries here. These are collectively called gauge symmetries. And so this overall is called a gauge theory. And an obvious question is, can we somehow unify these three symmetries into one overarching symmetry? So what are the problems of the standard model that I would point out at this stage? They're classifiable as purely conceptual problems, that is, things that bother us although they're not in conflict with experiment. And I would say one of these is the fact that there are many parameters of the standard model that you have to know in order to perform calculations. We'll see that there are actually 19 of them, and we don't understand at all the values of these parameters or constants of nature, and it's somehow worrying that there are all these numbers which we don't know how to relate to each other. Then there's no unification of these three forces of nature. Again, I mean, this is not a requirement. It's perfectly mathematically consistent that they should not be unified, but it kind of bothers us that we feel that there's something missing if things are not unified. There's a more technical problem, which I will mention, called the Higgs Mass Problem, and that is, it may seem surprising to you that since you've learned that the mass, or the mc squared, of the Higgs boson is 125 GeV, which is like a fairly heavy, I think like a tin atom, that this is classified as a light particle in the sense that we don't understand why the mass is so low. All the things we understand about quantum field theory suggest that it should be much bigger. And so there's, again, not an inconsistency, but a puzzling feature of the standard model that the Higgs boson is a light particle in the sense that it has a mass comparable with all the other particles, being heavier than some and lighter than others, rather than much heavier. Now, observationally, there are clear defects of the standard model. That is, there are things missing which we know are there in the universe, and the classic things are dark matter and also dark energy, which make up the majority of the stuff in the universe. And so, in a sense, although we have this beautiful theory, it doesn't explain much about the universe as we actually see it. Another technical point is, if you look at the evolution of the universe, now this is not something have no expertise in, so I don't have time to go into it anyway, but it's difficult to understand actually, although there's not so much matter in the universe, why there's as much as there is, because the standard model as it stands would suggest that there should be even less, that most of the matter in the universe should have annihilated long ago and left purely radiation and dark energy. So that's another mystery that we need to understand. And finally, the standard model says that neutrinos do not have any mass. This again is quite a technical matter, but maybe I will have time to mention it a bit more later. But we know for sure that neutrinos do have mass, and so that's a missing feature of the model. So let's look at the parameters of the standard model first. Many free parameters. Here they are. Now, we don't need to bother too much about this column here, but here's the names of all the parameters. You see there are the masses of the so-called fermions, the quarks and leptons here, which are just some numbers that we don't understand at all. And what's more, they have a huge range. Even amongst the leptons, there's a factor of thousands between the heaviest and the lightest, and almost 100,000 between the mass of the heaviest quark and the lightest quark. The top and the up quark have a mass ratio which is huge, and we simply do not understand that. There are other parameters, more technical parameters also make up this 19. The ones at the bottom here, you've heard about the Higgs mass, we now know is 125. And then this thing V that Laura talked about, which tells us the background value of the Higgs field throughout the universe, is also some number here which we don't understand. So, what's the solution to this? Well, one idea that seems fairly obvious when you think about it is that somehow there should be some substructure which would mean that although we have all these different particles and all these different parameters, perhaps the particles are made of something simpler that would reduce the number of fundamental constants. That's of course been the case when we've gone from atomic physics down to nuclear physics, and now we know that the nucleons, the protons and neutrons that make atomic nuclei are made of quarks, so that's simplification. The whole of chemistry came down to a few elementary objects, but we still feel that there are too many of them and that there should be perhaps some substructure. However, there isn't any really consistent theory extension of the standard model that would fit in with this idea, but of course it's a very good idea to look for substructure of quarks and indeed the other particles in the standard model, and I'm sure we will hear in the next talk how one would look for that. So just because theorists don't have a consistent idea of how to implement this substructure, of course, may simply be because we're too stupid, and we should rely on experiment to look for things to give us some guidance. So let's look at the major observational defect of the standard model, which is the absence of dark matter. Now, dark matter makes up about 21% of the universe. There's 4% of normal matter, that is the stuff we're made of and stars are made of, all the other visible stuff. There's all this dark energy here about which I won't have much to say because I think it's fair to say there are not very well developed ideas of what this actually is at the moment. On the other hand, dark matter, we have a lot of ideas about which need to be tested, in particular at the Large Hadron Collider. So why do we think there's this dark matter now? Joe this morning showed this plot. This is the plot of the velocity of stars, actually not just stars but gas, in this spiral galaxy here, which is called M33. This is one of the companion galaxies of our own. It's a mere 3 million light years away, and if you plot the velocities of the stars and the gas as a function of their distance from the center of the galaxy, then you find that instead of going down, as you would expect from the distribution of visible matter in the galaxy, they actually rise, actually keep on rising as far as we can tell as you go out further and further from the center of the galaxy. And I have a simulation here which has been giving me some trouble, but let me just try it anyway. It's gone a funny color again, but after a while it will go natural color. And on the left you see a galaxy which has only the matter which is visible, and so the periphery of the galaxy is going more slowly than the central parts, whereas the one on the right, let me run it again, the one on the right has the distribution shown below here, which is the velocity is more or less constant as you go out. So you can see the outer arms are going much faster than in this case here. And that's a signal that there's more matter that we can't see, which is actually extending out and probably beyond the visible galaxy itself, which is actually making up the bulk of the matter in the galaxy. As I said, there are about 5 times more dark matter than ordinary matter in the universe. So another good example of the evidence for dark matter is a so-called bullet cluster, which is 2 much more distant but colliding galaxies here. And what happens when galaxies collide, there are several examples, but this is perhaps the best one, is that the gas which makes up the bulk of the visible ordinary matter in the galaxy interacts between the 2 galaxies and gets slowed down, whereas the stars and the dark matter keep going. And so when you look at the colliding galaxies, you see the gas here which has been held back, but the plot of the matter distribution in the 2 galaxies shows that the 2 centers have kept on going relative to the gas. Now, the stars, as I've said, make up only a small fraction of the matter, so there's something else in this plot which is keeping going. In other words, it doesn't interact in the way that ordinary matter does, so it's a weakly interacting invisible component which is making up most of the matter. Now, how do we know that the matter is here? This is from this phenomenon called gravitational lensing, that we can tell from the bending of light from objects behind these galaxies that there is matter there which is bending the light. And let me just show in a different context how that bending works. Now, let's consider what this dark matter might be. An obvious thing that people thought of was that it might consist of just dark objects like black holes or dark stars or planets. We have to bear in mind that it's 5 times as much as the visible, so there's an awful lot of planets if that were the case. But let's suppose it is a planet. Then what happens is that if this planet or this dark object passes between our telescope somewhere and a star here, then it will bend the light. And that means that there will be an apparent brightening of the star when the object passes between the star and us. And then, of course, it will keep going, and then the object will fade again. So this is called microlensing because it's a transient phenomenon that just brightens the image of a star. And a good example is these data here from the so-called OGLE experiment. Nice name for such a thing, the optical gravitational lensing experiment. Ogles the various galaxies, and here's a nice example of microlensing. This is the time in days, and this is the brightness of some star, and you see that over a period of about 100 days it got much brighter and then faded away again, and so that is an example of a microlensing event. Now, I'm not an astronomer, so I don't know exactly what other possible explanations there could be, but apparently that is what they believe, that it is microlensing. So if there was all this dark matter in the form of lumps like that, black holes or planets or dark stars, you would get a lot of microlensing. And in fact, you see very, very little. And so the conclusion is that over a wide range of masses, the notion that dark matter consists of these lumps is ruled out. The other thing you might think of, which is already within the standard model, is neutrinos. There are neutrinos, after all. They're neutral objects which only interact weakly. But it turns out that from the history of the universe, it's very difficult to arrange a scenario in which there would be enough neutrinos and at the same time enough galaxies and in general structure in the universe that would agree with what we see right now. Neutrinos tend to prevent galaxies from forming. They are so-called stream. They're very light objects and they move very fast and tend to disrupt any structure which forms, and that is the basis on which people feel that neutrinos are excluded. So the best candidate for dark matter is what we call a WIMP, a weakly interacting massive particle. And the preferred mass for such a particle, in terms again of the evolution of the universe, the way it could get formed in the early universe, and the way it would interact and build structures like galaxies in the universe, is that it should be an object with a mass on the scale of 1 TeV, mc squared of the order of 1 TeV. Remember, the LHC energy for each beam is now 6.5 TeV, so this is an ideal machine for making such an object. I'll try to show you that in particular, say in supersymmetric theories, that's also a very natural mass that we would expect such an object to have. So the LHC could make them. For completeness, I should mention that there is a perfectly viable alternative, which I again don't have time to explain, but which is a particle called an axion. This is an ultralight, cold, that means low momentum, non-relativistic object, very much lighter even than electrons, probably not too different from maybe masses of neutrinos, but a slow-moving object with a very weak interaction, weaker than neutrinos, and these wouldn't be made by the LHC. So in a sense, if we don't see anything at the LHC, that would give more credibility to this so-called axion dark matter hypothesis. So, next topic that we would like to look into is a conceptual problem, which is the grand unification of those three interactions of the standard model. So let me go over the material on the three interactions. Remember, it's SU3, SU2, and U1. The SU3 is what we call the strong interaction, QCD, and that has some coupling which we'll call G3, the strength of the strong interaction. Normally we write it as G squared over 4 pi, which we call alpha, in analogy to E squared over 4 pi, which is the coupling of electromagnetism, which is 1 over 137. I should apologize here, I've left out factors of H bar and C. That's a habit of particle physicists. You saw, I think, that Fermi put them in the wrong place when he wrote the value of alpha anyway, so it's best to leave them out. Right, so alpha is actually a particular combination of the two electroweak couplings. This is one of the complications of the standard model, is that electromagnetism is a superposition of these two interactions here in this particular linear combination. The funny thing is that it turns out that the inverses of the couplings are more simply related than the couplings themselves. So alpha 3 is strong and 1 and 2 are electroweak. Now, another complication is that all these couplings are energy dependent, and let's try to understand why that is. Let's look at electromagnetism again. So suppose you have an electron sitting here. If it was in a medium, then it's straightforward to see that the electron polarizes the medium by attracting positive charges from the atoms or molecules or the lattice around it and repelling negative charges. And so if you draw a sphere around the electron at any point, then the total charge inside is somewhat less than the actual charge, the so-called bare charge of the electron sitting here in the middle. So you have so-called polarization of the medium, and actually the same thing happens in a vacuum. This is a bit more surprising because it's purely quantum mechanical, but what happens is that there are virtual electron-positron pairs forming in the vacuum all the time, like bubbling away, and so again the electron will attract the positrons in these pairs which are forming and annihilating, and repel the electrons, and so the same effect appears in the vacuum. And so that means when you penetrate this shielding here by going to short distances, or alternatively when you probe the electron at high energies, as we've seen, high energy at the LHC is essential for probing short distances. So when you probe it at high energies, you find a bigger charge because you penetrate some of this shielding here. And so the charge, the effective charge of the electron, or the effective coupling alpha, the value of E squared, seems to increase as you go to higher energies. And that's been verified. If you probe at the energies of the order of the electron mass, then you find you still get 137, the static charge. If you go to energies of the order of the Z boson, then you find 1 over 128, you see, which is slightly bigger. And in fact, the calculation of this phenomenon gives you a simple formula here, which says that alpha goes inversely like the logarithm of the energy. Now, what you can calculate is you can't calculate this number A for each of the interactions. There's A1, A2, A3. These are constants that you have to measure, like 137 here we measure, and so we know the value of this A at some energy. But we can calculate these coefficients B, which tell us how it varies. So once we've measured it somewhere, we can tell you what it ought to be somewhere else. That's another great triumph of the standard model, that we know these numbers here for the three interactions. So you see, for, as I said, electromagnetism is actually a combination of interactions 1 and 2, and I've got a big negative number here for 1, and a smaller positive number here. So the net result is this B is negative for electromagnetism. That means this denominator is getting smaller as the energy increases, so the coupling is getting stronger. This is 1 over a decreasing number. Now, when you go to the strong interaction, you find exactly the opposite. You see the number here, B3, was computed to be plus 7, at least at high energies. It's just plus 7. This is a calculation that you have to do, and indeed was done by David Gross, who is right here. And these other gentlemen, for which they were awarded the Nobel Prize in 2004. So the calculation of B3 has terrific consequences, because it means a strong interaction gets weaker instead of stronger, because the sign of B3 is opposite for the strong interaction from the other interaction. So the strong interaction is strong at low energy, and the other interactions are weak at low energy, but they will tend to come together as you increase the energy. So it's a natural thought that maybe they will all come together at some energy, and we will have this grand unification that we've been looking for. So the grand vision would be something like this. Here's the strong interaction coming down. The SU2, the weak alpha 2, is actually also coming down, but at a different rate, so it gradually comes closer, and the U1 is rising up because we saw that the electromagnetism is increasing, and it's mostly U1. So maybe at some scale here they will all come together, and then perhaps they will proceed together here to some final superunification with gravity, which I'm sorry I forgot to label here, but here's gravity, very, very weak at our energies, but at high energies, at the so-called Planck scale, gravity is so strong that space-time tends to break down. I mean, the energy scale is comparable to the mass of a black hole at that scale, and so there has to be some grand unification beyond which, who knows, space and time cease to exist as we know them. Anyway, that's the grand vision. Now, what happens in the standard model is not quite that. So here's, I've plotted for convenience 1 over the coupling. So 1 over the coupling goes linearly with the logarithm. That's an easy thing to extrapolate. Here are the present values, and when you extrapolate them, well, it doesn't quite work. So it's not terribly bad, but it's obviously off because the crossing points are many orders of magnitude apart. So the standard model doesn't unify. The couplings that we find upsetting. I can't claim that it's anything wrong with it, but we feel that it's not satisfactory. So now let's go to a more technical problem, which is the mass of the Higgs boson. So the problem with the Higgs boson is that the mass we measure receives a lot of quantum corrections. The Higgs boson can come along and it can dissociate into a virtual particle-antiparticle pair, just like this vacuum polarization. In this case, this makes a contribution to the mass of the Higgs boson itself. And when you compute that, you find that it has a piece here which actually would diverge if you allowed the momenta of these, or the scale of these fluctuations, to correspond to an arbitrarily large energy or an arbitrarily small distance. So you have to suppose that something is changing at small distances and cutting off the divergence of this mass contribution, and then you find that this energy cutoff lambda enters, like in the quadratic form here, into the mass of the Higgs boson. So if you have some grand unified theory or something like that, then you would expect this to be of the order of the scale of the grand unified theory. And we saw before that that's up here at 10 to the 14, 15, 16 GeV. So that is a huge contribution that would, it's difficult to see how it would not enter into the mass of the Higgs boson. There's a logarithmic term here which is not such a disaster, but this one is a disaster. So now, of course, that may look catastrophic to you, but we're actually used to thinking of this kind of quantum contribution as being a sum of some bare mass, just like the bare electron charge that we saw in connection with the energy variation of the couplings. Maybe there's a bare mass here which actually is very, very large and cancels this very large negative contribution from the quantum fluctuations. But that would have to be a 30 decimal place cancellation in order to arrive at the low mass that we actually measure. So that seems to be a very fortuitous cancellation. And again, there's nothing conceptually wrong with it, except we feel that it's hard to believe. Of course, some people say, and in general I should have perhaps mentioned, that many of these defects of the standard model, like the big range of masses and the big correction to the Higgs mass, are inevitable if we wouldn't be here if they didn't happen. So there could be some multiverse, there could be many, many universes in which these numbers have different values, and it's only when miraculous cancellations like this occur in one particular universe that we get human beings to even discuss the problem. So that's the so-called anthropic approach, but that's not very much favored by physicists who would like to understand things rather than just sort of give up and say, well, that's the way they are. Now, there is a point, which is that if only there was another kind of spin-zero particle other than the Higgs boson itself, then it would make a contribution to the mass of the Higgs boson. And if you compute that, you will find that it has a plus sign times this cutoff lambda squared. So if by some miracle the coupling here was adjusted so that these quadratic terms would cancel, then you wouldn't have this problem. You would only have these logarithmic terms, which are much more modest corrections to the mass. Well, it may seem a miracle, but there is indeed a theory in which these couplings, lambda here and the one I called G squared before, are exactly right to cause this cancellation. And whenever that happens, it's usually because of a symmetry. As you heard there, we base a lot of our guesses about the universe on symmetry, and indeed if there's a symmetry you get so-called miraculous, apparently miraculous cancellations, because the symmetry requires these conditions in order to be satisfied. And that is exactly the case with supersymmetry. There's a relationship between spin-zero particles and these so-called fermions, the spin-a-half particles, such that all these couplings are related in exactly that way. So let's think about supersymmetry. So supersymmetry sounds like, when you first see it, it sounds like a really incredible idea, because you take all the particles of the standard model here and you say they all have partners which differ in spin. So the superpartners of the quarks are called squarks, leptons, sleptons, and then you have these gauge bosons. They have what are called gauginos, and these have a spin 1/2 unit less than their standard model partners. And then there is corresponding to the Higgs boson. This is an exception, that it's because it already has spin 0, its partner has a spin 1/2 greater. It actually turns out in supersymmetry that there are additional Higgs bosons, so that one of the striking predictions, in addition to this marvelous cancellation, is that there should be extra Higgs bosons around to be discovered. Now, of course, we don't see at the moment any of these extra particles. So if these are all partners of the standard model particles, and there's a symmetry, then we should see them. They should, if the symmetry were exact, then it should be the case that we see them at the same mass. And of course that's absurd. We don't see a spin-zero electron with the mass of the electron. If we did, the world would be very, very different. But it turns out that actually there's a very natural mechanism whereby these superpartners can acquire masses without going through this Higgs mechanism, which generates the masses of the standard model particles. They can get masses without breaking the symmetries of the standard model. So it's quite natural that the superpartners would have masses and the standard model particles would not have masses, because they can't get masses without breaking the gauge symmetry. They have no access to any other mechanism other than this interaction with the Higgs field. So there could be another source of mass which the superpartners can get, which is not available to standard model particles. So that's not a major problem, that they would all have masses, whereas their standard model partners wouldn't. And indeed, masses on the TeV scale, mc squared is of the order of TeV, would be quite natural from this kind of mechanism. And as we see, they would solve the Higgs Mass Problem, and what's more, they would lead to grand unification. Let me show you how that would work, because the presence of all these extra particles changes the way that these three couplings of the standard model evolve with energy. So indeed, because they're extra spin-zero particles, all the energy dependence of these couplings is altered in a similar way, and so they all come down and they all meet within the uncertainties. These actually show the uncertainties in the values of these couplings. They all meet at about 10 to the 16 GeV. So this is the so-called minimal supersymmetric standard model. This is actually the simplest implementation of supersymmetry that you could think of, and it was a very exciting discovery that this would be sufficient to unify the couplings. So we've seen that the supersymmetry would lead to grand unification. Now, what about the dark matter problem? Well, the dark matter problem also has a natural solution in supersymmetry because there are WIMPs in the standard model, in the supersymmetric standard model. Of course, these are the superpartners of the standard model gauge bosons and the Higgs boson. So there are these particles here which are neutral and weakly interacting, and they have masses, as I've said, probably on the TeV scale, so they would be ideal characters to provide the dark matter. And indeed, one can make very plausible scenarios in which the mechanism of evolution of the universe and the breaking of supersymmetry gives rise to just the right density in the universe of these objects. Now, of course, only one of them will be stable against decay, because the heavier ones can decay into the lightest one and emit some standard model particles. So that's what would happen, and so the lightest supersymmetric particle, whichever one of these it is, or whichever linear combination of these it is, would be the dark matter particle. So the lightest supersymmetric particle could be the dark matter candidate. And that, of course, so that's an object which should be produced at the LHC, because it should be within the mass range accessible at the LHC. It's a particle. It doesn't have strong interactions, but has electroweak interactions. There are plenty of particles like that that we make all the time at the LHC, standard model particles, so we better be able to make it also. Okay, and what it would look like is, as you'll hear, I'm sure, later, is missing transverse energy. Here's a view down the beam pipe of some event with a simulation of an event where there's a dark matter particle leaving here, and you see the momenta, which are measured by the directed energy of these tracks here, don't balance up because there's something recoiling there. So let me summarize. So how much time have I got? I've got 10 minutes? Okay. So I think what I'm going to do is I'm going to talk a bit about neutrino masses as well. So let me summarize what I've done so far. We've got many arbitrary parameters of the standard model. Perhaps that's an indication that there's some simpler substructure. Grand unification and the Higgs mass and dark matter could all be solved by supersymmetry, so that's a very appealing candidate for physics beyond the standard model. Dark matter, we really don't know what it is at the moment, and the two remaining topics here are related to neutrino masses, so maybe I can say a few words about that. Let me just mention that there are many other ideas that I haven't had a chance to talk about. For example, extra Higgs bosons, composite Higgs bosons, extra spatial dimensions, another very interesting possibility, and string theory, which in a sense could combine all these features together with supersymmetry at the much higher energy scale. So let me so we need more data, and perhaps we need the next machine. Anyway, let me go on, since I have a few minutes left, and talk about neutrino masses a bit. This is a rather technical issue, so I hope you won't get completely lost. But it is important, if only because the Nobel Prize last year was awarded for the discovery of neutrino masses, or at least the discovery of neutrino oscillations, which prove that neutrinos have mass. So why, first of all, what are neutrino oscillations? So remember, there are three species of neutrinos. There's electron neutrinos, muon neutrinos, and tau neutrinos, corresponding to the three families. And the amazing thing is that they all transform into each other. If you make a beam of neutrinos, then it oscillates between the three so-called flavors of neutrino as it goes along. And here's a plot of about one cycle of the oscillation as seen by the so-called Camland experiment, which is an experiment in which anti-electron neutrinos from a nuclear reactor, these come from the decay of fission products in a reactor, are detected at some distance by a huge detector which sees the interaction of these neutrinos with protons essentially to make positrons. Now, so what they measure as a function of actually distance divided by energy is the oscillation of the amount of electron antineutrinos in this beam. So, and as I show here, the oscillations are supposed to remind us that the flavor is changing as you go along. The spots on the snake are different flavors of neutrino. So how does it work? The problem is that these three flavor species of neutrino are mixtures of species of neutrino which have different masses. And if three particles have different masses, then if you produce them at a given energy, they have different momenta. And in quantum mechanics, if they have different momenta, they have different wavelengths. And then you get beats between the waves of the three species with a phase which goes like the difference in the inverse of the wavelength. Those of you who teach about waves will know that that's the kind of thing you get in sound waves of different frequencies. You get beats, but in this case the beats will be sensitive to the difference in mass squared. If you do the algebra here, the relativistic momentum algebra, then the phase, the oscillations depend on the mass squared difference, and L over E, that's the variable that we were plotting in the Camland data here. L over E measures the progress of the wave of a given energy. And experimentally, the three neutrinos have mass differences given by these two tiny numbers here. So the neutrino masses are very, very small. In fact, this is a rather busy slide, but the bottom line is that the neutrino masses divided by their corresponding lepton masses, charged lepton masses, say the electron, even if you put in the electron mass here, you find that the neutrino masses are a millionth of those of the, probably a millionth of those of the charged leptons. So that is a great mystery. What is this huge mass gap? First of all, where does this mass come from anyway, and why is it so tiny? So this is an attempt to explain some idea about neutrino mass. So the problem is that electroweak interactions are what we call chiral. They treat the two states of spin-1/2 particles differently, where the two states of spin-1/2 particles are classified according to this property called chirality, which is a relativistically invariant, so an intrinsic property of the state, which is only corresponding to its handedness as a spinning object when it moves at the speed of light. So this chirality is sort of like handedness, but only when things move at the speed of light. But still we call it left and right-handed. That's just the label. What we have to bear in mind, it's not actually the handedness of the spin when the particle is massive. And mass is an interaction that converts left to right and vice versa. So that's achieved in the Standard Model by interaction with the Higgs field. The Higgs field converts left chiral particles into right chiral particles and vice versa. And it does that by eating up some property of the particles which is called isospin. So, for example, when you have an electron, a left electron has a property called isospin equals 1/2. This is the SU2 interaction quantum number, and it has a charge minus E, of course, and when it interacts with the Higgs field eats up 1/2 unit of isospin and changes it into a right electron. So that's the way we think about the interaction with the Higgs field. So if we had a neutrino mass, the simplest thing is we have to introduce a right-handed neutrino, which is actually absent in the standard model. And then we would say, well, okay, the left-handed neutrino, like the left-handed electron, has I equals a half, but it has no charge. So the Higgs field would eat up this half a unit and make it into an object with no isospin and no charge. So it would be a sterile particle with no standard model interactions whatsoever. So that would be something superfluous in the standard model. It would be a very hard object to detect because it wouldn't interact through any of the standard model gauge interactions. And of course then there's no explanation of why the mass would be very much less than the electron mass. But since this thing nu r has no standard model quantum numbers, there's another option for giving a mass to the neutrino, and that is the so-called Majorana mass. The Majorana mass can change a right-handed neutrino into its antiparticle, which behaves like a left particle. And then this is okay from the standard model quantum numbers because it just changes 0 to 0. On the other hand, it changes a particle into an antiparticle, so it's quite different from our ordinary concept of mass. And it turns out that this mass could be at the grand unified scale, and then it would mix with the mass obtained through this standard so-called Dirac mechanism, or in our case, interaction with the Higgs field. And it turns out that the observed neutrinos would be mixtures of these left and right particles, which would have masses either up at the grand unified scale or at a scale of m squared over m. The ratio between the square of the Dirac mass and the Majorana mass, which is 10 to the minus 3 electron volts, which is just what you need to explain the data. And this is called the Seesaw mechanism, which was invented by two Japanese physicists, Fukugita and Yanagita. So here's the seesaw. Here's this very big chiral right-handed neutrino here, which is pushing down the seesaw, and that is very heavy at the gut scale, and it pushes up to a very light value of the mass, the observed neutrino, to this very low mass. So that would be a funny thing that this heavy object actually succeeds in explaining the very light neutrino mass. And I should mention that that also raises a possibility of explaining the amount of matter in the universe from decay of these very heavy neutrinos. So that's now my summary with that piece included, that we have three things I've talked about: possible substructure, supersymmetry, and heavy neutrinos. I should say heavy neutrinos have no chance of being made at the LHC, so I think we can, that's one of the reasons why I left this as an optional item at the end, but I think it's a very important aspect of the standard model, and it's been in the news recently because of the Nobel Prize. Okay, so thanks for your continued attention.
Thank you very much, Bryan. I think we have time for a couple of questions, so here's the first one.
My question is just, all right, if the grand unification scale is 10 to the 16th GeV, what could you hope to actually see of that? I mean, what empirical evidence would there be that something is there?
Well, if we could ever build such a machine, then the hope is that these three interactions would be all part of one interaction. I mean, a very simple, or the simplest idea, which doesn't quite work, is that these three symmetries would become unified in a symmetry called SU5, of which they're all subsymmetries, and then the leptons and the quarks could all be put together in families, just like the quarks are at the moment. And so all the particles which we now have separated into each family into quarks and leptons would become unified into one group altogether. And so they would, above that energy, they would all have the same interactions. So there wouldn't be any difference anymore between quarks and leptons.
Could you also see photons decaying?
You would in that, yes. So that's right. Most of these. So if you put the quarks and the leptons together in a family, then you have the danger that there will be an interaction which changes a quark into a lepton. And that means the proton could decay into some lighter state containing leptons, right? So that would be a disaster because there wouldn't be any protons. So you have to make sure that the lifetime of the proton is much bigger than the lifetime of the universe, much, much bigger. Otherwise you would have seen lots of proton decays. And in fact, many of these neutrino experiments are also incidentally looking for proton decay because they just sit there for years with a huge volume of detector waiting to see something. And if a proton decayed, they would see it. But in supersymmetric grand unified theories, you can actually get around this pretty well, and you can arrange things so that the lifetime of the proton is much bigger than the present limit. So, so far we're okay, but ultimately if quarks and leptons are in the same family, then there will eventually be proton decay. Yeah.
Okay, we have another question right here.
So you mentioned on one of the slides that string theory
Yes.
would fit in with supersymmetry. So would supersymmetry be like a subset of string theory, or would it be the other way around, or how would they tie into each other?
Well, string theory, I don't know. David Gross will be able to tell you much more about string theory than I can, but there are plenty of scenarios in which string theory gives rise to or contains supersymmetry and also extra spatial dimensions that I mentioned. In fact, string theories are usually, or consistent string theories require extra dimensions, but then they get compactified, they get squeezed down, so we don't see them at present scales. But certainly supersymmetry is a natural feature of string theories.
Okay, do we have some more questions? There's a question right here.
Just if supersymmetry turns out to exist in some form, would that really simplify the standard model? Or would we just have extra parameters?
You would have a whole bunch of extra parameters, yeah. This is one of the problems with as I mentioned, we know it's broken because the superpartners have masses and the standard model particles have much lower masses on the whole. So there is clearly we have to understand how the symmetry is broken in order to know what the superpartner masses ought to be. But if we don't understand how the symmetry is broken, then we have an arbitrary parameter for the many arbitrary parameters for all these masses of the superpartners. So we certainly need experimental help to sort that out. Yeah.
So on the other hand, maybe supersymmetry would help with dark matter. Is that not right?
Supersymmetry would help with dark matter because there would be a dark matter particle which we could produce experimentally. Yeah.
There was a question right here.
I don't know if you discussed this or mentioned this. The LHC, they've looked at the energy levels to see potentially some of these supersymmetric particles, and they haven't seen anything yet. And
Right.
and perhaps we need to scale up the energy more to.
Yeah, that's right.
Is there
There's
a limit
concept
to the range
called
where we rule it out? I guess what I meant. At what point would we rule out the supersymmetric particles?
Right. There's a concept called naturalness, which is to some extent subjective, which is, where do you... So I said the superpartner masses ought to be around the TeV scale, right? So does that mean 1 or 3 or 5 or 8 or, at what stage do you run out of belief that this mechanism is going to work? Obviously, the higher the superparticle masses, the more delicate cancellations you start to need to get the Higgs mass to be what it is now, because those logarithmic terms still depend on the superpartner masses, and they don't, you get into trouble if the superpartners are very heavy. Obviously, if they're very heavy, then they influence things less, and you start to run into the same old problems. So there will come a time where possibly within the lifetime of the LHC that people will say, if we haven't seen supersymmetry yet, then maybe it wasn't such a great idea. On the other hand, there are indications of other things which, maybe we got it completely wrong. Maybe something else is taking care of all these problems, and we're just too dumb to see what it is.
Okay, we have other questions here.
Theoretically, what kind of framework do you need to understand physics beyond 10 to the 16 GeV? Is it a phase transition from where no space-time to space-time occurs? And
it is a kind of, this grand unified symmetry would be broken at that scale, so there would be some mechanism of breaking it, like there is in the standard model symmetries, maybe. There would be some around that energy scale. There would be a profound change in the physics, and then above that scale, everything would be much more symmetric.
so do we know how to describe physics beyond 10 to the...
Well, that's the job of string theory.
Also, if there's no space-time, so there is no...
Beyond the Planck scale, yes. I mean, Planck scale, I think nobody would consider at the moment. We know how to go because the very structure of space-time becomes ill-defined beyond that scale. At least within the existing theory of gravitation. I'm afraid I didn't mention gravity because, again, we don't have a quantum theory of gravity, so we don't know how to deal with that.
So does it in any way answer the question that how did the initial mass come into picture when the universe was created? Where did it come from originally? Was it the space-time singularity that gave rise?
Sure,
Was it the general relativity? That's why we
something happened, before that there wasn't any space, there wasn't any time, there wasn't, certainly there wasn't this universe. There may have been others going on somewhere else, but as far as we're concerned, there isn't anything before. We just say it was like a bubble suddenly appearing somewhere.
But it should have mass, right?
Yeah, well, it had a lot of energy, that's for sure.
Okay, I think we could do one more question if we have one. Yes, right here.
Yeah, just a question about the very low energy particles. You said that you wouldn't expect them to be produced in the Large Hadron Collider.
Yes.
But we heard earlier the speaker said that they weren't interesting. There were low energy particles that they would just try to filter out in order to see the more interesting higher energy particles. Is it that they're not being produced, or they're being produced in great abundance, or
Yeah. So perhaps I didn't say it clearly enough. The low energy things that they're trying to get rid of in the experiments are standard model particles which happen to have low momenta, right? They have, they have whatever masses they have, but they're traveling very slowly or relatively slowly, and so they curve up a lot in the magnetic fields and they make a lot of junk. They're very copiously produced, but they're just standard model particles. But the axion doesn't have the conventional standard model interactions, so it wouldn't be produced in those collisions. But not at any appreciable rate, I guess. There are ways of making them, but
Okay, I think we're ready for our break, so I'd like to thank Bryan Weber very much for a wonderful talk.